Welcome back, everyone. We are going to do sections 8.2, 8.3, and 8.4 today. I wanted to start with an overview of what we learned in section 8.1, the process of going through a hypothesis testing. So we're going to start with a summary. And our step one is our null hypothesis and our alternative hypothesis. And our null hypothesis is going to be either P equals straight line on that. It's going to be mu equals, that one's a little complicated. And not in this video, but eventually in the next video, we will be doing sigma equals. So those are going to be our null hypotheses as we're going through this testing process. Now, I want to point out that when we're using, when we just have one of these and not two, chapter 9 is if we were comparing proportions or means or and so on. But we will be using for our tests is going to be, for this one, it's going to be one prop z test. And for mu, it gets confusing. If sigma is known, we're going to use a z test. And separate from that, if sigma is not known, then we're going to be using a t-test. And here, for the sigma, the population standard deviation, we don't have a test that's built in. We have to do that one manually. Our null hypothesis, let's go back to here, is going to be, for the proportions, it's going to be P is bigger than, P is less than, or P is not equal to. For mu, it's going to be mu is bigger than, mu is less than, or mu is not equal to. And same with sigma. Sigma is greater than, sigma is less than, and sigma is not equal to. And just as a quick reminder, if it is greater than, that is a right tail test. It's less than, it's left-tailed. And not equal to is two-tailed. So that's basically our rundown of how we're going to be going for for step one. Step two is we need to find the test statistic. And that means that we're going to be running the one proportion z test that you see up here, the z test or the t test. And this also means that we're going to be finding the p-value. Step three. We're going to actually come to either decide to use, the reason I'm stumbling is because I'm going to actually apply both, but we need to do the p-value method or the critical value method. And again, I'm going to blend the two so much so that it's going to seem like it's all the same thing, which is really what it should be. Step four. Is make a decision. And that is going to be reject the null hypothesis or fail to reject the null hypothesis. And for that, we will need our alpha. So again, if the p-value is less than alpha, then we're going to reject the null hypothesis. If the p-value is bigger than the alpha, then we're going to fail to reject. And here we go. So let's start with section 8.2 in our notes. So we're going to test a claim about a mean. So we're going to be testing mu. And for these, sigma is going to be known. And that means for us that we're going to be using z-test. All right, so a couple of requirements. Sigma is known, normally distributed, and it's known and n is bigger than 30. That's only if we don't know if it's normally distributed or not. Okay, let's jump into it. These ones are paragraph long, so just try to relax. We'll try to identify what we can out of this. Before changes to its management staff, an automobile assembly line operation had scheduled mean completion time of 13.7 minutes. This is our null hypothesis. The standard deviation of the completion times was 1.1 minutes. That is our sigma. That is them telling us that we know sigma is 1.1 minutes. An analyst at the company suspects that under new management, the mean completion time mu is now less than 13.7. So let's manage that. Less than 13.7 minutes. To test this claim, a random sample of 27 completion times under new management was taken by the analyst. So what they're telling us is that n in this case is 27, had a sample mean x bar of 13.5 minutes, and our alpha in this case is 10%. All right, so we are definitely using a z-test statistic in this case. And let's set up our picture here. I always like drawing a picture. To me, it gives a much cleaner view of what's happening. Less than means that it's a left tail. So we are here. And to find the critical value, I'm going to use inverse norm 0.1. So inverse norm 0.1. So this looks like it's going to be negative 1.28155. All right, now we have all of our information. Let's go to the test statistic. Once again, I'm going to be using, in this case, a z-test. So I'm going to go to stat, tests, z-test, and we have a commercial. Sorry, this may take a minute. This is going to be a long one, I can tell. By the way, I do not endorse or condone or whatever any of these games. It's just something I get for getting a free calculator. All right, so maybe we can move on. All right, done. All right, so we are using statistics. Mu in this case is 13.7. Our standard deviation is 1.1. X bar is over here, that is 13.5. N in this case is 27. This is a less than scenario. And let's see what we get. So here is our test statistic. So Z is about negative 0.94475. And the p-value that we're getting is here, 0.172. And I want to point out that that is definitely bigger than our alpha. And that's the big deal here. That's our comparison. Also, I want to point out that our test statistic is not in the critical region. It's over here somewhere, negative 0.9. So both the test statistic is not in the critical region, and at the same time, our alpha, or our p-value is bigger than our alpha. So that tells us that we are going to fail to reject our null hypothesis, meaning we're sticking with 13.7 minutes is the mean time. So can we support that it's under that? No. No, we cannot in this case. So let's do another one. An old medical textbook states that the mean sodium level for healthy adults is 140. So that's going to be our null hypothesis. Milli equals per liter of blood. A medical researcher believes that because of modern dietary habits, the mean sodium level for healthy adults, mu, now differs from that. Now, when it says differs, that's code for us that it's not equal to 140, which means we're going to have, excuse me, a two-tailed test. It says a random sample, so N is 44 in this case, of healthy adults is evaluated. The mean sodium level for the sample is 141. Is known the population standard deviation of the adult levels, so it tells us that sigma is known to be 12. Assume that the population is normally distributed. Can we conclude the 10% level? Okay, so let's draw our picture. And this is Z. This is now a two-tail, which means that we have to split the alpha up into two separate pieces. So half of the 10%, the alpha is 0.10 here and here. And to get these critical values, we're going to have to do inverse norm 0.05 and inverse norm 1 minus 0.05 to give us the right one. So let's see what we get. Inverse norm 0.05. So I'm getting negative 1.64485 and inverse norm of 1 minus 0.05 is the positive version of that. Okay, we are set up. We are going to be using a z-test because the population standard deviation is known. And so we are going to be running, once again, a z-test. So stat, tests, z-test. And let's go to the top here. So we are at 140. Sigma is 12. X bar is 141. N is 44. This is a not equal to scenario. And here we are. So our test statistic Z in this case is about 0.55277. Critical values we already got. So let's color code this. Negative 1.64485 and 1.64485. And we can clearly see, it doesn't ask for the p-value, but we can certainly get the p-value from this. So the p-value we can see here is about 0.5804. And we can see that that is clearly, so this one's using the critical value method, but we can see that this is clearly bigger than 0.1. And also, to use the other method, we can see that this is definitely not in the critical region. Both conclude that we're going to fail to reject. The null hypothesis. So can we conclude that it differs? No, we can't. Now, if it was the other way around and we rejected the null hypothesis, then yes, we would conclude that. All right. Part 3, we are now testing the mean when sigma is not known. Once again, that means that we're using a t-test. So t-test is going to be our distribution in this case. So t-test. There we are. Let's go through this scenario. Thanks to an initiative to recruit top students, an administrator at a college claims that this year's entering class must have a greater mean IQ score than that of entering class from previous years. The administrator tests a random sample of 20, so there is our n, and I want to make it clear, n is 20, which means our degrees of freedom, because it's a t-test, now is going to be 19. So we'll just need to keep that in mind. Of this year's entering students, it finds that their mean IQ score is 114. So there's our X bar. With a standard deviation of 14. So that's a S, not a sigma, of 14. College records indicate that the mean score for students the previous years is 113. So that's going to mean that mu is equal to 113. Is there enough evidence to conclude that the population's mean is greater than that? So our alternative is here. This is definitely going to be a t-test. And remember, our t-distribution looks a lot like our z-distribution. It's a nice, pretty bell-shaped curve. And because it's greater than, this is going to be a right tail test. There's our critical region at 5%. And to find the critical value, I'm going to use inverse t of 1 minus 0.05, and then I need the degrees of freedom as well. Remember, t-distribution depends on the degrees of freedom. So inverse t, 1 minus, and it's 1 minus because with the TI versions, it's only left tail, so we have to do the 1 minus. And 19. There it is. So I have, for my critical value, 1.729. All right. So we are now going to find the test statistic. And once again, I want to remind us that we're going to be using a t-test for this one. So stat tests, t-tests, and another commercial. This one should close very quickly. There we go. So let's go to the top. We're using statistics in this case. And mu in this case is 113. And we have 114. Sample standard deviation is 14. And in this case is 20. And this is a right tail test that's greater than. And calculate. So here is our test statistic. So t is about 0.3194-ish. Critical value we already found, so they're using the critical value method for this one. That's fine. And we can clearly see that this is not in the critical region. We're way over here. I want to point out that the p-value is about 0.376, which is clearly larger than our alpha. So our test statistic is not in the critical region and the p-value is larger than, so our conclusion is we're going to once again fail to reject the null hypothesis. So can we conclude that it's greater than previous years? No, we cannot. All right. The Journal de Botanique reported that the mean height of begonias grown while being treated with a particular nutrient is 45 centimeters. So that is going to be our null hypothesis. To check whether this is still accurate, heights are measured for a random sample that of 18. So is 18, which means our degrees of freedom is 17. A sample of 18 begonias grown while being treated with a nutrient. The sample mean and sample standard deviation measurements are, the mean is 51, sample standard deviation is 12. Assume that the heights of begonias are approximately normally distributed. Based on the sample, can be concluded the population height, mean height of treated begonias is different from that. So different is code for us to mean not equal to, which means we are going to have a two-tailed test. Again, this is a t-distribution. And this is going to be two-tailed, which means I'm going to take my alpha, which is 0.1, and break it up into two pieces. So half of it is over here. The other half is over here. And I want to find the critical values, so that's going to be inverse t, 0.05, with the degrees of freedom of 17, and inverse t, 1 minus 0.05 degrees of freedom of 17. So let's find those real quick. Inverse t, 0.05, comma 17. So I'm getting negative 1.7396, and inverse t of 1 minus 0.05, comma 17. There's the positive version of that, 1.7396. All right, so now we are going to run our t-test. So let's go to stat test t-test. Let's start at the beginning. So we are at 45. The mean is at 51. Sample standard deviation is 12. N is 18. And this is a not equal to. And here is our test statistic. So this is a t. Test statistic is right there. That's 2.1213. And in this case, they're doing the p-value, which is 0.048896. And our alpha is 0.1. So this is definitely less than our alpha. And we can clearly see that this test statistic is definitely in the rejection region. So in this case, we are going to reject the null hypothesis. So can it be concluded that the mean height of treated begonias is different from that? Yes, we can. Is what we can conclude from that. And now we're going to move in testing a claim about a proportion. So far we've done testing a claim about a mean, knowing the population standard deviation, and then not knowing the population standard deviation. And now we're going to test a claim about a proportion. And in the following video, we'll test a claim about a standard deviation or variance. So here we are, testing a claim about a proportion. Sample observations are simple random sample. Conditions for the binomial distribution are satisfied, and NP and Q are both bigger than 5. We're not going to test that every time, but we could if we needed to. All right, so a marriage counselor has traditionally seen that the proportion P of all married couples for whom her communication program can prevent divorce is 76%. So that is going to be our null hypothesis. After making some recent changes, the marriage counselor now claims her program can prevent divorce in more than 76%. So the claim is here. In a random sample of 220 married couples, so this means that N is 220, X is 183 stayed together. Based on the samples, are enough evidence to support at the 1% level. Okay. Proportions are always z-tests. In fact, we're going to be using a 1 proportion z-test. Be how we find our test statistic, but before we do that, z distribution, and this is greater than, which means it's going to be a right tail test. Here we are at the 1%, 0.01. So to find the critical value, I'm going to have to use inverse norm of 1 minus 0.01. Remember, inverse norm is only area to the left. Let's see what we get. Inverse norm, 1 minus 0.01. So we're over here at 2.3263. All right, so we are going to run a 1 proportion z-test in this case. 1 prop z-test, you can see it number 5 there. And we're going to start here at 0.76. X is the 183, that's the number of successes. N is 220. And this is a right tail test. Here we go. Here is our test statistic. .4942. Critical value we've already found, so they're going to be using the critical value method. That is the z is 2.3263. And I want to point out that the p-value is about 0.0063, which is less than our alpha. And we can see that this is just slightly in the rejection zone there. So both the p-value and the test statistic and critical value are going to give us that we are going to reject the null hypothesis. Oops. Which means, is there enough evidence to support the claim? Yeah. So this divorce or marriage counselor's system is working. Good for them, or her, I guess. All right, so last example for this video. A college claims that the proportion P of students who commute more than 15 minutes to school is less than 25%. So this means that P is 0.25 and P is less than 0.25. So there's our null hypothesis. A researcher wants to test this, a random sample of 260 students, so n equals 260. At this college is selected. It is found that 53 commute, so that's our x, that's our number of successes, commute more than 15 minutes to school. Is there enough evidence to support the college claim at the 1% significance level? All right, so let's set this up again. And these are always a z-test. And because this is less than, that's going to be a left-tailed test. So this is 0.01. So I need to use inverse norm. To get our critical value. This is a negative 2.3263. And so once again, we are going to run a one proportion z-test. And another commercial. Sorry, this video is plagued with commercials. All right, so let's start at the beginning here. We are at 0.025 or 0.25. X in this case is the 53. Oops, 53. And in this case is 260. This is a less than scenario. Let's see what we get. So our test statistic is Z is about negative 1.7187. Our p-value is 0.0428. And I can see right away that that is, what is our alpha? Oh, this is way bigger than our alpha. Excuse me. I also want to notice that this is not in the critical region. And the p-value is bigger than our alpha, which means we are going to fail to reject the null hypothesis. So is there enough evidence to support the claim that it's less than 25%? Nope, there is not. Well, I hope you found this useful.